I think that's us. Is that us? I think that's us.
That's my name there.
Yes. Hello everyone, my name is Chris Stewart. This is Emily Brunsden. Emily is an astronomer at the University of York. I'm not an astronomer. I'm the useful idiot in tonight's conversation. I'm a local science communicator. I work with researchers at the university on trying to turn research and science generally into things that are digestible by the rest of the world. Emily is on the side of actually producing the knowledge and then turning into something which is digestible for the rest of the world. And the two of us, since 2018,
that's going to age us badly.
which is a ridiculous amount of time, have been doing a little podcast called Syzygy. Hands up if you've ever heard the Syzygy podcast.
Woo!
For those of you listening on the podcast, we're recording this for posterity, and everyone in the room just put their hands up, didn't you? Yes, you did.
Absolutely.
We've done a few live events, and that's pretty normal, actually. But we enjoy it, don't we? It's not about the audience size. Thank you all for coming out and doing some astronomy with us here tonight. It's a bit odd to be doing an astronomy. I mean, doing an astronomy podcast is weird, because podcasts are audio-based and astronomy is very visual, and so that's already kind of strange. This is extra strange because we're doing astronomy when it's still daylight outside and we're inside, which is, like, that just doesn't work. Emily, what are we doing here? Why are we here? What's going on?
Well, as my lovely punny title, I think, kind of tries to sum it up, this is a little bit about basically taking a moment to look up into the skies, very, very literally, and appreciate a little bit of what's going on in our universe based on what you can see. So we're kind of going to give you a little bit of a whistle-stop tour through some of the really interesting things that you can go and have a look at in the night sky. That sometimes
in the sky.
happens.
In the sky, yeah.
And I have to confess, when I thought about this concept, I thought, oh yeah, this will be great. We're going to talk about auroras, and we're going to talk about comets, and we're going to talk about Jupiter. And then I suddenly realized that the Festival of Ideas is in June. And I thought, we're going to have to rethink this a little bit.
You can't really tell people, just go outside and have a look up into the sky and see all these amazing things, when the night is literally about 13 seconds long at this time of year. I come from Australia. I'm still getting used to the fact that it never gets dark until you get to winter, and then it never gets light. How do you people survive? Shall we begin by taking your title literally?
Absolutely, yes.
Could everyone work with us here? Could it just take a moment, look up. Just take a moment to appreciate where we are right now. I don't think I've ever been associated with a place this awesome in my life. I've worked in a lot of venues, we've done live shows in a lot of great places, but being here in this hall, 1415, okay, maybe this place wasn't necessarily built in 1415. I don't know whether it was or not. We should get a historian. If only there was someone who could tell us. It was built in 1415. This hall was built in 1415, people. Look up at that ceiling. It's what an amazing place to be able to do a public talk in which we're encouraging people to look up. So just take that in.
It's got to be one of the most beautiful ceilings in York.
Yeah.
Easy,
yeah.
Right?
What was going on in 14...
If we're going to have a ceiling above us, yeah, let's go with this one.
Yeah,
I like this one.
I'll take that. So any insider knowledge on what was going on in 1415 in the world of astronomy?
Well, I think it's actually really fitting when you think about going back that far, because we didn't have telescopes. This is before we had Galileo, this is before we had Copernicus, this is before we had Kepler, before we had really the same picture of the universe that we have now. So we're going to pull on that a little bit, because the things that we're talking about tonight are things that you don't need a fancy instrument to go out and appreciate in the sky. These are all things you can go and look at just with your naked eye, as astronomers would have in 1415.
Yeah. Can I just also point out, before we move on from the fact that we're in this hall, I just read on a sign over here that these windows were unveiled by Judi Dench. I'm sitting where Judi Dench was standing. How cool is that?
It's very cool.
Anyway, back to the story. So where do we begin? We're talking about astronomy that you can, when it's dark enough, go outside and look up into the sky. And one of the most obvious things that we could point you towards, I guess, would be the moon. So shall we start there?
Let's start with the moon. Who saw the moon tonight when they came here?
The moon's not out in the daytime, Emily. What are you talking about? That's ridiculous.
Well, of course it does, because every one of us in this room has seen the moon in the daytime. And I'm glad nobody put their hand up and lied that they saw the moon on the way here, because it's not going to rise until about 1 a.m. So this is good. The audience is a trustworthy bunch. We
Good.
can keep with them. But the interesting thing with the moon, I think, as you said, is that you do see it obviously at the night, but you also see it in the day. So it's a perfect summer object to continue with. And I've got a son who is 4 years old, and every time he sees the moon, he giggles and points at me and says, "Hey, what's the moon doing hanging out in the daytime? What's it doing?" It is this classical nighttime object, but it's not really a nighttime object. And I'm going to talk about that in just a minute. But before I did that, I wanted to present to you something that has, I think, made me struggle a bit, and I imagine made you struggle a bit with the moon. And that is, I think everybody has a personal connection to the moon, right? You've looked at the moon and you've tried to see the man in the moon, the cheese in the moon, the mouse on the moon. Some people say there's a dog catching a ball. Some people say there's a T-Rex. I don't know. But the thing is that the moon looks different depending on where you are.
It does. It's true.
And forgive me, I know we're not in Scotland, but close enough, right, to York. This is the difference between the typical image you would see of the moon from Scotland and from New Zealand. And of course, what do you notice?
Kiwi, Aussie.
Yeah, well,
we're used to that one. We're used to that one. And so, I don't know about you, I grew up with the man in the moon, right? And you're looking at the moon going, I guess, sure, okay, looking at the one on the right. It was only when I got to the northern hemisphere that I went, oh, that! Oh, that makes much more sense. Yeah.
I only see a T-Rex, I'm afraid.
Well, yeah.
That's all I see.
You are a bit odd.
But of course, this is our first little clue that actually the moon looks different depending on where you are standing on the Earth. And why is that? It's because we're working in this three-dimensional geometry where we have a sphere. We have people in the northern hemisphere standing upside down in that sphere, people in the southern hemisphere doing it the right way around.
Correct. Yeah.
And so therefore you see this flipped image of the moon. And even just that very simple thing, I think, thinking about what the perspective is, the fact that this wonderful celestial object that's just so easy to go out and spot, often you're spotting it just by accident, is actually connected to this fact that we are actually one whole ball sphere going through this dance with our moon orbiting us.
We were just picking up on that and pulling that thread a little bit. We were just talking before we came live on microphone to you. I have lived on both sides of the planet over much of my life at different times. And I grew up knowing that the sun goes across the sky in the north. And so I've been here 11 years, I'm still 180 degrees out. Intuitively, I know exactly where north is, and then I have to tell myself, and now reverse it. Still, to this day, 11 years later. It's very odd.
It's amazing how we have that intuition.
Same reason.
From
yeah.
where we're going. Yeah.
Anyway, back to the moon.
But then, yeah, we can go a little bit further with the moon and start, well, actually, no, I wanted to share this photo first, sorry. This is not a photo taken with a big fancy telescope. This is not a photo taken from space. This is a photo taken from my back garden with my phone.
It's all right. That's okay.
I'm very proud of that. And I am not a photographer. I am not an astrophotographer. I know very little about doing all that sort of fancy stuff. But just proving, I guess, a very small point that you don't need to go out with fancy equipment. The moon is big, it's bright. If you point your phone at it, you can get a fantastic shot, actually, of just the moon.
Well done, we're all impressed.
Excellent,
Yeah,
thank you. I'll produce signed copies. No. So the wonderful thing about the moon is that it's not only telling us about this wonderful dance that the moon and the Earth play, of course, but it's the sun as well. So the next time you see the moon, it's probably not going to be a full moon, like the next time you see it, chances. So next time you see it, have a think about what's actually happening. Why is the moon not a full moon? Why has it got this glowing face, or half face, or quarter face, this phase of the moon? And it's because of course, our friend the sun. And if there's a very nice thought, I think, when we go out and look at the moon. If you look at the moon and it's half full or some version of not quite full, you can therefore immediately tell where the sun is, because it's the sun that's shining onto that face of the moon that you might only be able to see half of, a quarter of, or at new or full moon, 100% or 0% of. And so just by that simple, oh, look, it's a half moon, that half is the one that's illuminated, you can track that back to exactly where the sun is in the sky. And it's a lovely little piece of geometry. If you're at half moon, then the sun's 90 degrees away. If you're at full or new moon, it's 180 degrees away.
Yeah,
so
it's something that I still do today. If I see a half moon, I'll sort of go, and the sun's over there, which it is. So well done. Yes, I got that right.
And it's wonderful, because I think it's often quite hard to imagine that we live in this three-dimensional world. I really struggle with the three-dimensional aspect of a lot of astronomy. But it's one of those things where if you sit there and look at it and you think about it and you then pull that out to the 3D geometry, it's that nice connection between what you are directly seeing and our place in our local part of the solar system with this, our interplay with the sun and the moon. I really like that.
Yeah, nice.
Yeah. Something so ordinary and everyday, but is actually something, a wonderful piece of physics, this dance between the three bodies in the sky.
So, anything else about the moon, or shall we move on to our next part of the evening?
Yeah, that's a nice transition.
Yeah, nice segue.
Yeah, you've been practicing that one.
I have. Well, you did tell me earlier you didn't have a segue, so I thought I'd just throw that in there.
I can try for one. Let's try for one.
Give it a shot. Give it a shot. Segue coming.
Actually, I'm going to need a little bit of help because I'm bad with directions like you are. Which way is east?
East from here. Do we have consensus?
Is it through this window? Oh, perfect.
Right through there.
Look at that wonderful window. This is the east. And in the eastern sky, in the summer, there's a really, really wonderful constellation. It's, well, one set of stars. It's one of the most beautiful and easy to find groups of stars, I think, in the summer. So this is something that is called the summer triangle. Which is not, as I thought when Emily was mentioning it when we were putting this together, the summer triangle being the bikini bottoms. That's not what we're talking about. You know, we're not talking about getting a beach-ready body. We're talking about astronomical constellations. I've never heard of a summer triangle. What's a summer triangle? Well, it's three of the brightest stars in the sky that you're going to see in the eastern part during the summer. And it's really familiar to a lot of people because it's the kind of thing where you've gone to your campsite, your tent's blown away. I don't know what's happened with the British weather, but suddenly the sky is cleared and you're lying there at 11
Sorry, have you been
at
camping in this country? That doesn't happen.
It happened once.
Right, okay.
It's that sense. Maybe you did it even as a kid. You lay out in the lawn in your garden, or you were walking home rather late one night from the pub. Whatever it is, it's one of the easiest things to see in the summer. We tend to be outside a little bit more, to be fair, looking at the sky in the summer. So it's a really nice thing. And so it's due east, so you can figure out where the sun is sort of rising and go from there. And it's the three stars. So the three stars are called Vega, Deneb, and Altair. It's actually not a constellation, technically. There are official constellations, if you like, that astronomers have set in the night sky. And this is not one constellation. It's actually what we call an asterism, or just a random group of stars. And what is it, as opposed to all the other constellations, which are random groups of stars? But sure. All of them are random groups of stars. But anyway, so, but there are three different parts of this constellation. There's all three constellations that are part of this summer triangle. You've got Cygnus, which is the swan, which is the one that's sort of drawn with the blue lines here. Deneb is the bum of the swan. We can all see that, right? That's a swan, clearly. I can see that. That's the best one. I'm not even going to go into how they get the other ones because, anyway. Vega is one of the brightest stars in the summer sky. It is the constellation of Lyra, the harp. And Altair is from the constellation of Aquila, which is the eagle. And I do have a lovely drawing of how those are obviously made up of those constellations. Sure. No, I've got nothing. Anyway. If you do happen to go out and look at the summer triangle tonight, what you will see is that Vega and Altair are basically straight up and down above each other tonight. That does rotate as the seasons and the night sky goes on. But right at sunset tonight, you will see Vega and Altair above each other. So yeah, it's a lovely set of stars. And you kind of alluded to it before, Chris. We think about these constellations or groups of stars as being these really nice connected things. Yeah, I'm sorry, but these are just pure figments of someone's imagination.
Yeah, I mean, I was going to ask you, like, to an astronomer, constellations are, that's fine, but there's nothing real there.
No.
Like, they're not just, separated as we see it across the dome of the sky. They're separated by ridiculous amounts of space,
well,
right?
That's right, yeah. In fact, in this case, you've got Vega, Deneb, and Altair. They're 3 stars. They actually look similarly bright in the night sky. But if I was to tell you the distances to these stars, we've got the closest one is actually Altair, which is around 17 light years away. So that means that light, the fastest thing there is going to take 17 years to get there. So it's quite a way, but in terms of stars, it's kind of semi-close, really. It's quite reasonably close. We've then got Vega, which is about 25 light years away, so kind of similar. And then you've got Deneb. Do you want to take a guess how far away Deneb is?
17, 25 light years, 40.
More than 1,000.
Okay.
So it's a crazy difference. So if you tried to imagine that in 3D, which would be a terrible thing because I think you'd go a bit funny. Basically Deneb is 1,000 times further away than those other 2 stars. And it's just simply that Deneb is a really, really, really bright star, just really, 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 really far away, that it looks to be the same brightness as the other 2.
But we, in our minds, just go, that's a triangle. We'll call that the summer triangle. That's a pattern.
Yeah.
We love patterns. That's a swan. Apparently.
So they say. So it's a wonder, to then take that idea a little bit further, then think about when you're looking at stars, it doesn't even have to be the summer triangle, that you are looking at this collection of things that we are seeing just purely because of our position in space. Right? There's nothing pure about these constellations. If you go a couple of stars down the road, all those constellations are completely busted, and you're going to have to come up with new ones. Hopefully better ones than whatever that harp is supposed to be. Maybe.
Give them a break. They were working with what they had.
Yeah. So that you're already, just by thinking about those 3 stars that look kind of the same brightness in the sky, you're getting this real sense of not only is the universe this 3D structure that extends beyond, but you're also getting a sense of actually stars can do all sorts of wonderful different things, because clearly those 2 stars that are closer to us are less bright than that 1 star that's 1,000 light years away. So you're already getting that kind of sense of real diversity.
Yeah, and we have a very specific perspective on the universe. It's unique to us, and it gives us these patterns in the sky, which we make believe are animals and harps and so on. But yeah, far more interesting to think, as you say, hop a couple of stars across, and it's completely different. You get to make up your own set of patterns. Yeah.
And then the fact that it's even summer. I mean, the fact that you can see this triangle in the summer. It's not a winter object. Even that little idea, I'm playing on that idea, tells us something about our relationship again with actually the sun. Because constellations, what you can see in the sky changes quite dramatically between the summer and the winter. And it's purely just because of our little Earth going around a very, very large sun. So this is actually a sketch of the constellations of the zodiac. So 12 constellations. I'm not going to ask you your star sign, and I'm not going to tell you that you're going to come into money, I'm afraid. But nonetheless, the constellations of the zodiac are real astronomical things, and they are in the sky. They do form part of our set of 88 constellations. And what makes the zodiac special, if you like, is nothing to do with whether or not you were born in June or September, but actually it's the path of the sun's apparent motion through the sky. So as we go on our little orbit, on Earth's orbit around the sun, you get to see the sun appears to go through different constellations as you go through. So that's what that little arrow is, going from the Earth to the sun to, in this case, I don't know, what is it, a monkey? I don't know. A lion?
It's a goat, isn't it?
Oh, I don't know.
What's up there?
I mean, the zodiac constellations are no better than...
I don't know.
Anyway. So it's the sun's path through the sky, which is an important thing. It's called the ecliptic. It tells us about how this Earth is moving around the sun. But in this case, what we're looking at in terms of the summer triangle is actually not the thing that's towards the sun, because if you try and look at a constellation that's behind the sun, guess what? You can't see it.
Don't try to look at, no.
Don't look at the sun first of all, that hurts.
Turn the other way and look at the thing that's not towards the sun.
Look at the thing that's behind you.
The scorpion, for example.
In this case, exactly, it's Scorpio. So that's why, and then if you imagine that little Earth going around in that circle, 6 months later, you're going to see a different set of constellations. And that wonderful, again, orbital motion. It's very simple, but it's something that in 1415, coming back to the Hall, didn't exist as a concept at all.
It's lovely that we've mapped out in stories this really quite fundamental thing to our motion in the universe and motion in the solar system. We've mapped out this thing that we have observed over millennia, which is that these same patterns come at different times of the year. That must be significant. We'd better make shapes out of them and tell stories about them. That's what we do as humans. We're really good at that. Not knowing that we were doing this, that we were mapping out the ecliptic of our path around the sun. That's really cool.
It's very cool. It is very cool. And so I think I really like the summer triangle, and I like it for some other reasons as well. So as you're going to probably tell, I'm going to give you some homework after this. And your homework is going to be to go out sometime this summer. It could be tonight. I mean, it's actually not looking that bad. And look for the summer triangle and look at these 3 stars. And actually, I want you to also look at a 4th star. It's not quite as bright or as impressive as these 3 stars, Vega, Deneb, and Altair. It's a kind of, I don't know, what's that about? Less than quarter of the way between Vega and Altair.
Yeah, a bit less than that.
But if you think, draw an imaginary line. I'm sorry, these purple lines do not appear in the sky when you go to look at them. But if you draw that imaginary line, it's about sort of just under a quarter, maybe 20% the distance between Vega and Altair. There's another star that's actually the 2nd brightest star in the constellation of Lyra. Okay. We call it Beta Lyrae, because it's beta, it's the 2nd Greek letter, so it's the 2nd brightest star in Lyra. But it's got another special name, which is called Sheliak.
And I'm guessing that you're telling us this because you have a point, that it's not just, we have a triangle, but let's put another dot on it.
Yeah, and the rest of my slides, by the way, are the next star, and the next star, and the next star, and the next star, until we've gone through no.
None of you are going home, we're here all night.
Yep. No, this is actually a really special star, and it's a special star because it's got a really special connection to York. So I wonder if anyone has been to Treasurer's House, for example, which is just literally over there. Treasurer's House. At one stage in his life, there was a young fellow called John Goodrick who was living in Treasurer's House at the time. And
handsome chap.
He was actually, well, at least the painting was. And and I know he's pointing to a thing in the book, and there's all these meanings that you're supposed to get out of these paintings, and you'll have to ask someone much more clever than I am what all these meanings are. But this is supposed to be a painting of him in Treasurer's House in York, where he did at least some of his observations of different stars. You can go find his blue plaque. It's, again, just up the road. And he was here in the 1700s. Particularly, he published a paper in, it was a bit later than the plaque kind of suggests here, but it was, 1784 was the publication that I'm going to be talking about. Because on the blue plaque, it talks about he looked at 2 variable stars, including Algol and Delta Cephei. Now, these are both really important variable stars that I'm not going to talk about, because he also looked at Sheliak. And Sheliak is a wonderful variable star. Now, to the best of our knowledge, John Goodrick did not have a telescope. He wasn't doing his observations through any kind of instrument. He was purely doing these things with the naked eye.
Just going out and doing that.
Just as you guys are going to go and do tonight, right? But Sheliak is such a cool star because it changes brightness.
So when you say you're talking about variable stars,
yes,
stars can vary in different ways.
They can.
So
yeah.
what?
So this is, we're talking about the brightness changing of the star over time. So, and the wonderful thing about this type of variable star is that it doesn't vary over thousands, millions, billions of years. It varies over the course of about 13 days, which even in cloudy York gives you an opportunity to start looking at the brightness changes of the star.
But hang on, sorry, back up. John's going out. He's doing this, And he's able to determine the variability of a star over a 13-day period just by looking at it.
Yep.
How much does it vary by? Like, is it turning off and on completely?
It's not, but it's varying in brightness by nearly 2.5 times.
Okay.
So it's
you would notice
a pretty big change. And what happens, of course, is when you are used to doing this kind of work, this kind of variable star astronomy at this time, you would train yourself to be really, really good at measuring by eye how bright a star is. And there are people who do this to this day, amateur astronomers, who will go out and be able to look at a star and tell you that one is this bright and that one is this bright.
But that's not, I mean, just think about that for a minute. That's not a bad effort, right? Is to be able to go out and go, of all the stars, that one's slightly dimmer tonight.
It's amazing.
I'll come and have a look at that again in 2 weeks' time and see what it's like. Like, that's just extraordinary. Absolutely extraordinary. Well done, John.
I mean, he's very patient.
I'd give him a blue plaque.
Yeah, absolutely. And so we can come to then, once you can go out and look at it tonight. In fact, the next time it is going to be at its minimum brightness is tomorrow.
Right.
So we're nicely in the cycle.
There you go.
You can go and see it quite dim tonight.
So tomorrow night, find someone who's not here and take them out and point to the star and then just drop on them that fact that that star there is actually at its minimum brightness. We won't see that again for another 13 days, actually. I think that'll get you a lot of points, I think, at your next party. No? Okay.
Not in my circles.
Just the parties that I go to. Fine.
But the question is then why? Why is the star varying in brightness?
I thought you meant why was John doing that. No, why was the star?
No one can explain why John was doing
yeah.
it. I mean, he was a very talented man. But no, why is the star doing it? It's actually, if you are familiar with the story of John Goodrich, it's exactly the same reason as Algol. So he discovered a class of variable stars, which to this day are called Algol class stars. And what they are actually is they are not one star in the sky at all, but they are two stars. So these are what we call binary systems. And what happens, you've got two stars orbiting each other, and one of them moves in front of the other. And if you're not really convinced by my fist movements, I've got a very expensive video.
That was quite good, I mean, to be fair.
Made by ESO.
They have a slightly larger budget than we do.
Which will show this.
If it starts.
There's always a bit of a delay.
Here we go.
So here's our two stars, and what the little graph there is plotting is the brightness over time. And you actually get two little blips in the brightness, one when the little star goes behind the big star, and one when the big star goes behind the little star. What we're going to see tomorrow is the big dip, basically.
So the little star going behind the big star. Yeah. That's so cool. So drop that in. When they're blown away by your ability to even do this at all, you can then, of course, throw in, it's like, and of course, the obvious reason that it's doing that is because it's a binary system, right? And you can do the hand thing.
And scientifically,
I'm helping your social lives here.
Yeah, well, maybe until I drop the next one in.
Yeah.
Scientifically, these are some of the most important systems that we can study, these binaries, because they tell us very, very nice information. These are stars that were probably born at the same time, and so you can make really nice comparisons. If one star is doing this, why is it doing something different to the other star? They can also tell us about gravity. We can get mass measurements, just in the same way as you can measure the mass of the Earth as it goes around the sun and the moon. You can get really lovely measurements of the gravity of these stars and get their masses, which is actually really hard to do for other stars. So they're really super important for calibrating lots of modern astronomy to this day.
So yay for, what kind of stars are they? They're
eclipsing binaries.
Eclipsing binaries. Yay for eclipsing binaries.
Yeah, so they're very, very cool.
All right, you have a segue.
Well, I do have a segue.
Drop it in.
Well, we're talking about here quite large changes in the amount of light that you're getting from a particular object. Something that you can see with the night sky. I'm going to transition to something that I'm going to ask you to look at in the summer triangle, where you're going to look at a patch of sky where you're not going to see anything at all.
This one's less interesting to talk to your friend about. See this patch where there's nothing in it? But trust me, this is worth it.
Yeah. So here's our summer triangle on the side here. So we've got Altair at the bottom, Vega and Deneb. So there's this patch of sky, which is this funny shape. It's a plus, it's like a fat plus sign. And the little circle in there is the size of the full moon, just for scale in our drawing there.
And just by the by, the moon in the sky, like the full moon in the sky, really big, right? Like it's huge. Absolutely. You look at it, say, look at the full moon tonight. It's tiny. Like next time you see a full moon, just take a step back a little bit and it's like, yeah, but there's a lot of sky. Like it's really small in the sky.
You can cover the full moon up with your thumb at arm's distance.
And that's nonsense, right? Like full moon's like that. Oh, it's that big. It's that big. And that's it on the sky there.
Yeah, so that little boxy bit of sky has a really interesting fact about it. Does anyone know what's in that little boxy bit of sky? Anyone? This is a good one. I like challenging questions. What if I told you that to this date we've found, actually I wrote this number down, let's be precise, 6,291 exoplanets. These are planets going around other stars, other star systems, other planetary systems.
So like other solar systems, like ours.
44% of them are in that box in the sky.
Why would that box have all of the planets in it, Emily? That's ridiculous.
Is there this magical place in our galaxy that only planets exist?
No, I'm guessing there's some other reason.
No, it's because this is where we went looking for.
Oh, right.
So this turns out to be where we pointed our space telescope called Kepler. So Kepler was, 2009 to 2013. It did its main observations. So for 4 years, Kepler, its one job, the space telescope, was to stare at that patch of sky and look for very, very tiny changes in brightness.
Quick question. I'm guessing everyone here has heard of Hubble, the Hubble Space Telescope. Yes, I can see lots of nods. Very famous space telescope. How many people here have heard of the Kepler Space Telescope? Okay, a reasonable number of people, but fewer than Hubble, right? So Hubble gets all the glory because it takes specky pictures of the universe. But Kepler spotted planets.
Yeah.
Like it's awesome.
I mean, this is why we needed a robot telescope in space to do this, because there's no astronomer in the world. Even Goodrick would not stare at the same patch of sky for 4 years uninterrupted.
I reckon if you'd asked him, I reckon he would have given it a shot.
And made a note of the brightness of every single star in that field, yeah?
Quick question. Why there?
Because it's a good place to look. No, it was chosen very specifically and a little bit politically, which I won't go into the politics.
There's always politics.
The scientific reason it was chosen is it's actually a piece of sky that has a reasonable amount of stars in it, but not too many. So if you actually look in some parts of the sky, there's more stars clustered because of the setup of our galaxy, the disk of our galaxy. So we didn't want them to be too close together because then they're all crowded and you can't see one for another. They all just blur into one sort of blobby mess, even with the best space telescopes. But we wanted to have quite a lot of stars to find as many exoplanets as we could. So that's why we picked there.
Good. Carry on.
And then, so we looked in this patch of sky. Kepler very, very diligently looked at that patch of sky, taking an image about every 2 minutes for 4 years, measuring the brightnesses of all these stars. And what Kepler, the telescope, was looking for was, again, changes in brightness, just like Goodrick, and actually for the same mechanical reason as Goodrick. But instead of looking for changes in brightness of about 2.5 times, Kepler was looking at very slight dimmings of these stars of less than 1%. And that's why you need a big space telescope and a fancy camera.
One of these things can be seen by a dude over here doing that, and one of these things can be seen by a space robot staring at a patch of sky for how long?
4 years.
4 years. So one of these problems is harder than the other. Yeah?
And so why this small drop? Because planets, and there's a little kind of graphic at the top of the illustration here.
Well, there will be when you put it on.
Oh, sorry.
There you go.
There we go. There's Kepler there. There we go. Lovely space telescope. So what you're seeing here is Kepler, this illustration looming around in space, pointing itself towards a star. And in front of that star, you see a little black circle, and that is the planet moving in between us and the star that's behind it. And that is what's causing this little 1% drop in the light just like the eclipsing binary does, the same mechanics. It's just planets, really tiny and not bright because they're not emitting their own light.
So that graph that you had before with it doing the big drop in brightness, imagine this exactly the same thing, except that drop is, what did you say? Less than a percent. Less than a percent of the height. So it's just a tiny, tiny little blip that no one would ever notice unless you were a robot in space.
But it was a brilliant mission and it was incredibly successful. So Kepler went out to say, I'm going to stare at this patch of sky, I'm going to look at all these stars and I'm going to count how many of them have planets. And from that we can do some fancy maths and extrapolate how many planets we think there are in our galaxy.
Yeah, I mean, if there's this many in this bit, extrapolate that to all of it and you get, well, a lot, really.
You do.
That's the answer I think they came up with was quite a few.
Well, in total, but when you boil it down to how many planets per star...
Okay, now hang on. How many stars in the Milky Way?
About 300 billion. 300
billion stars. How many planets per star do we think?
About one.
About one per star.
Average.
On average.
On average.
Some don't have any, maybe. Some have lots, like us.
Yeah.
But one per star, so 300 billion.
So that was Kepler's job. It was to answer that, basically that one question. Are planets common or are they rare? And it certainly found out that they are common.
Turns out.
And that's why we're up to 6,000 odd that we have now discovered, these other worlds around other stars. And if you want to know more...
Yes. have we piqued your interest in exoplanets? Because if you want to know more, we're going to be talking about that this coming Sunday. We've got another talk, 7:30 Sunday, down at the Ron Cook Hub at University Heslington East Campus. Come and see us talking about just that, just the exoplanets bit, not the other stuff.
Exactly.
Back to this.
Yes. So that is Kepler looking at really, really tiny drops. So coming back to what you're seeing in the sky, look at that patch of empty sky and think that nearly half of all the other worlds that we know to exist around other stars come from that little patch because this heroic telescope took the time to look for them.
This friend that you're out walking with tomorrow night pointing this stuff out, they are going to be absolutely floored by your sudden dramatic increase in astronomical knowledge about a very small random patch of sky.
And even if you can't see that patch of sky, just point at a star and say,
it's probably
there's a planet around that.
Yeah.
And you're probably right.
Statistically, one. Yeah.
Exactly.
That one too, and that one, and that one.
Yeah. Exactly. You can do wonderful things.
Yeah. So we talked about a few things that you can go out and have a look at in the sky, a few things that you can go out and have a look at that isn't there, but you can say what, or like, you can't see, but you can say what would be there if you were a robot in space looking for 4 years. You get the idea. But last bit of the talk tonight, shall we bring it back to something that you can see, but maybe you need to be a little bit careful about doing so? Yes,
absolutely. And it's certainly something that you don't need to be patient as Goodrick to observe. You don't have to observe for 13 days. It's something that is actually a massive change in brightness, bigger than even 2.5 times change in brightness.
But it's the same kind of idea.
It is. Well, it turns out it's all the same physics.
It's what's known as a syzygy.
It is.
Name of our podcast.
And
Syzygy.
So if you are lucky enough to look out on Wednesday the 12th of August into the western sky and look for the sun, kind of around about dinner time, tea time. I'm sorry, I'm not Yorkshire enough to get those two correct.
What time of night?
Evening meal.
Whatever you call your evening meal, about them.
Then this is kind of what you're going to see. And this is what we're going to see is a partial solar eclipse. So this summer we are getting really treated to not having quite a total solar eclipse. Those are quite rare for any individual location, but even this partial eclipse is quite rare. But it's going to be something like 92% of the sun will be covered up by the moon. And this is a syzygy, as you say.
Yeah, a syzygy, the name of our podcast. Worst name for a podcast in the world because it's spelled S-Y-Z-Y-G-Y, and no one will ever remember that. But it is an alignment of 3 celestial bodies, right? Earth, Moon, Sun. Or Earth, Sun, Moons also. Or exoplanet, star, us, or etc. So this is a syzygy.
It is, yeah.
And when is this again?
So this is the 12th of August.
So not far away.
It's going to start, eclipses are sort of gentle things. They don't sort of happen like that. It will start at about 12 minutes past 6. Now, at that point, the sun will be about 20 degrees up in the sky. So it's not super high.
Really?
So you're going to need to be somewhere where you can see the western horizon really nicely. And if you want to know what 20 degrees is, if you take your arm at arm's length and put out to both your fingers, you can try it. You can try it. This is a hang 10. Oh, come on, I was going to get you to do thumbs up there. Yeah, that distance between your little finger and your thumb at arm's length is about 20 degrees.
That's 20 degrees, so that much from the horizon.
So that much above the horizon. So if you're scouting out throughout the rest of June, July, then look for somewhere where you can see that far above the western horizon. And that's actually the sun's setting, of course, at that time. It's setting at a slow angle, but by the time you get to this point, when it's at maximum coverage, then it's going to be only around 12 degrees, which is about
half of that.
Yeah, or a fist, if you do a fist.
But the point is, it'll be above the horizon, you'll be able to see it, and so why wouldn't you?
Yeah.
Why wouldn't you? Unless it's cloudy, in which case, oh well.
It will go darker. It will go.
Well, because 92% of the sun,
it's quite a lot.
Still leaves a reasonable amount of very, very, very bright star, but it's definitely going to get darker.
Absolutely.
Yeah.
So this is a picture of something that might be what we see, particularly if you are looking, now of course we're going to say don't look at the sun without protection here, because this is one of the things you do need some technology to really appreciate, but that technology can be as simple as some solar glasses, right? Something that's going to block the light so that your eyes don't get fried by
Where would one
sun.
get solar glasses?
Well, we're going to do some events, but I'm going to put a pin in that later.
Okay.
So if you are interested in doing some of this observing with us, then there will be, if you follow the University of York public lecture series, then you will see something about that, hopefully coming up soon. But yes, you can get them online, you can get them freely, they're freely available for not much cost, because they're just a little bit of cardboard with some filters.
They're a little bit like the glasses you take to get at a 3D movie. In fact,
don't use those.
No, that would be bad.
Yeah.
But it's like, we're not talking welder's helmet or anything like that. This is not complex stuff.
So that's the kind of view that we might expect to see of the sun and the moon, which is a pretty amazing thing, to see the sun in a crescent like that, just like you would expect from a phase of the moon. Now, I did sort of anticipate that actually we might see something like this, because it's, of course, Yorkshire.
Let's face it. We'd be lucky to see that,
be honest.
I think.
And what I'm really, really hoping is that we don't see something like this.
Yeah.
However, I have avoided saying that astronomers' bane, of course, is the clouds, and the clouds are fairly common in Yorkshire. But, you never know. We might be quite lucky.
You should have been an atmospheric scientist instead.
Sometimes I wonder. But then sort of, I guess, coming back to a little bit, so those eclipses, even in 1415, it was possible without telescopes, without calculators, without computers, without AI, to predict when eclipses are going to happen. And it just so happens, this is a cool fact, that in 1415, when the year that this hall was built, in fact, only a couple of days hence from now, on the 7th of June, 1415, there was a partial solar eclipse.
What?
That was really actually quite similar to this one here.
That's nuts.
I know.
What are the odds?
Isn't that amazing?
So, okay, there's your finale for going out with your friend tomorrow night. Once they've had their brain exploded by everything else, you can just say, by the way, and just drop in the 1415. If you were here with John, arm around his shoulder, you would have noticed a partial eclipse of the sun.
Well, John's ancestors.
Well, yeah.
Yeah. So that's kind of where we wanted to get you to. So think about starting to look at the sky. You might not be looking at a night sky that's like this in the summer, but there are still wonderful astronomical objects to go out and see. And so if you did imagine looking up into this beautiful ceiling and taking that roof off, there are things that you can go out and look at that will tell you about the relationship between the Earth, the Moon, and the Sun. There are things that will tell you about our place in the universe in terms of the stars that are around us in the summer triangle. There are things that tell us about the dynamic nature of the universe, like Shellyak changing on just 13 days. It's a very human timescale. That's not the billions of years it takes for stars and planets to do their thing. And then you can think about the wonderful explosion of other worlds that we have to tantalize our imaginations. Come along on Sunday.
Sunday night, 7:30, Ron Cook Hub.
Or you can just enjoy the marvelous phenomenon, natural phenomenon of a partial solar eclipse that we're lucky enough to get, hopefully if the clouds are not there in August.
And can I just point out, if you get really into it, you could come and do your PhD with Emily, just like Tom sitting on the rock there. That's a real photo.
It is a photo, yeah.
Like, that's not photoshopped.
Nope.
He took that long exposure, presumably.
Yeah.
But yeah, Tom has just submitted his PhD thesis with his supervisor, one of his supervisors. So well done, Tom.
My first PhD student.
I think that was probably just after he handed his thesis in, and he's just zen on a rock going, thank God for that.
Yeah, so I guess to wrap up, it leaves us to just say, if you're not, I guess, totally freaked out by the things that we've said, and you're very anti our Antipodean accents, then
I think what Emily's trying to say is, if you've enjoyed this, you can get more things like this at syzygy.fm, which is where our podcast is, and on all good podcast collectors and so on. So yeah, go and have a listen. We've been doing this since 2018. We've got like 125 or something episodes. There's been a bit of a gap since the last one, but we're working on that. I promise we do still exist.
Yeah.
We talk about everything from this kind of thing, looking up into the sky, to the beginnings of the universe, the end of the universe. Is there life on other planets? You think of it in the universe, we're doing an episode about it. So we'd love to have you along.
Absolutely. And also you'll see this Astro Campus logo. The Astro Campus is the observatory at the University of York. I'm the director, so I have to give it a good plug. This is an observatory that is open to the public for free. We have observing sessions over the winter. So I'm afraid you're going to have to park your anticipation. But if you want to come and use our telescopes and see what we can even see in the deeper universe with those telescopes, you're very welcome to book on and come along to one of our observing sessions in the winter time.
So that's basically what we wanted to talk about tonight. Thank you very much for your attention, for coming along. It's great to be in this hall and to have such an attentive and some of you very early crowd. People were here like when the doors opened half an hour before we started. Like, you're super keen. I just wanted to say thank you, and thank you to everyone on the team who's put this together, from the fabulous AV people at the university and got us the table and the chairs, to everyone who has helped put this thing together and who were about to help us manage a bit of Q&A. But just before we do that, a big thank you to everyone. Thank you, Emily. It's nice to be back doing this podcast again. And for those of you who haven't checked it out yet, there's so much going on at the Festival of Ideas over the next couple of weeks. So many things happening on every night of the week that you'd be mad not to go and check it out, particularly this Sunday at 7:30 at the Ron Cook Hub. So that's all from us. Thank you very much. If you got any questions, ask away.
Yeah.
Thank you. All right. I think we've got our first question here in the third row. I think you had your hand up. Did you have your hand up? Yes, okay. First question over. If everyone could wait for the microphone to come down. We have the fabulous Ollie and Emily just right beside you. So wait for the microphone and then ask away.
I'm very sorry, this is not actually a question. Forgive me.
Is this a comment, not a question?
No, it's not a comment, it's a suggestion. Can I just suggest to everybody, who probably knows already, that just north of here there's a place called the North York Moors National Park.
Yes, there is.
Which is a designated dark skies area. And if you get the chance to go up there, it'll be a lot easier to see some of these magnificent sky objects. So just think about it. It's a nice trip out. Thanks very much.
Very true, very true. I'd applaud that. Yes. It's a fabulous place. All right, down in the front row here. And I love your t-shirt, by the way.
Thank you. What is the most recently coined constellation?
Oh, the most recently coined. When's the last time we invented one? Could we do it now?
There was, now I'm not going to be able to tell you specific dates off the top of my head. The 88 constellations were set by the International Astronomical Union some time ago, but not so long ago that they don't include things like a microscope and a telescope.
Okay.
So I'm afraid that's your window. If I took a stab, it would be kind of 1800s, something like that.
It's not happening all the time.
No.
But it's not ancient Greece either.
So actually, all those constellations actually go beyond the pretty picture borders. They actually have, this is very boring, but they have very sharp lines, boxes basically, and all those boxes between them cover the entire night sky.
Right.
So there's no more space. We've covered it.
It's pretty rare that someone
like a
goes,
patchwork
hang on,
quilt,
this bit, no one's done anything with this bit. I think I see a hamster. We'll have it.
You're most
have the
welcome
hamster.
to.
Okay, all right, I'll put in an application.
Yeah.
Thank you. Any more questions? What have we got? Down in the front row again.
So we've got billions of stars and planets.
Yes. Hundreds of billions.
At one time, Uranus was classed as a planet.
Pluto?
Pluto. Sorry.
Yeah, that's right.
Yeah. What is the basic difference and why was it downgraded?
Oh, you are opening a box of hurt there.
No.
Wow. I mean, like, as the non-astronomer here, the number of times that this has come up, where not just that question specifically, but astronomers naming and defining things. And I will say to Emily, so I mean, I'm a bit confused. Like, when you say, you know, this particular astronomical thing, like, why is it like that? And there'll be this long pause, and Emily will say, history, I don't know, it's just like that. So Emily, planets, Pluto,
well, actually, out
what's
of
going
all
on?
the things we have, we don't have a very good definition of a star. I'm sorry, we don't have a very
It's
good...
literally your job.
We don't have a very good definition of an exoplanet.
Good.
We don't even have a very good definition of a galaxy.
Well done.
What we do have a very good and solid definition for is a planet in our solar system. This is the one thing we've done.
Great. So we've caught up with
millennia of
basically...
astronomical history.
We've caught up with basically about 10,000 years ago,
Yeah.
is what you're saying. And we haven't really
moved on.
moved on since then. Well done.
I'll give you the very formal reason. So there are 3 things that a planet needs to do in our solar system to be called a planet. It needs to, 1, orbit the sun. Right, good.
Check. Pluto. Yep.
It needs to, what's the second one? Needs to form, it has to have self-gravitation to form a sphere. Basically, it means it's got to be big enough that it's not a lumpy potato like some of the asteroids and bits of comets and whatever other nonsense we have in the solar system.
Yeah, you get above a big enough size and your gravitational mass pulls you into a sphere, right?
Yep.
And so you've got to do that.
Yep. So
Pluto, tick.
it does that as well.
Doing well.
What Pluto fails on is the third one, which is clears your own orbit. So what that means is you've got to be the biggest, baddest thing in your orbit around the sun so that you dominate that whole region gravitationally.
And what is Pluto not dominating?
Charon, for example.
Bloody Charon.
But also other things. Pluto actually's orbit at times crosses inside the orbit of Neptune as well. So it will actually become closer to the sun than Neptune at particular times in its orbit. And there's also a whole lot of bunch of stuff that Pluto has not been able to clear out of its orbit, little bits of space debris and blah, 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 blah. So for that reason, it fails, basically. And it's a good thing, I guess it does, because we really got to the point of, if we include Pluto as a planet, we're going to have to include Ceres, which is the biggest asteroid, which is also spherical and also orbits the sun. And then we started finding more and more stuff, and we were like, we've now got 17 and a half planets, and our children's books are wrong, and what are we going to do?
It's just easier to just cut it off there, I think is.
Yeah.
But I mean, what I love is that people really do get passionate about this. Like, there are people who say, that's not fair. Like, I grew up with Pluto as a planet. You can't just take it away from me. And even amongst the astronomical community, there were passionate debates about this. And I think that's fabulous. I think that's wonderful about a rock that, since we discovered it, hasn't even done one orbit around the sun. You know, we get passionate about things. We're a weird species. Any more questions? This gentleman over here.
So of the planets in the summer triangle, of the stars in the summer triangle, can we say with some certainty whether any of them or all of them has a planetary system?
Have we looked at any of those 3?
Not to my knowledge, but... So the thing is with planets, is when you're talking about that eclipse of the planet, so the planet moving in front of the star so that we detect that little blip of light, we have to have that orbital alignment just right? So it has to be on a perfect alignment so that that planet moves in front of us and that star. Now, if the planet's going around like this,
As you're looking at it, yeah.
Yeah, as you guys are looking at it, you're never going to see it. It's never going to cross in front of that star. So they may well have planets. In fact, it's very likely that they do.
Statistically, one.
Yeah, but we're not ever going to be able to detect every planet around every star. We're limited to the techniques, and all of our techniques require some kind of alignment for that to happen.
I mean, just as a sense, like we were talking about that cross shape where we saw so many exoplanets, right? But like, how many stars are there? Like, we saw a few thousand, but how many stars are there in that cross? Now, I know that that's a really hard question to answer. You might have a number for me, I don't know.
I think it's around 300,000 stars that were actively monitored, and there's been a few more that have come back in.
So that's a few thousand out of 300,000 just in that bit. Like, the chances are slim that looking at any given star, even if it has loads of planets, that we would see them, which is why you've got to point a robot at a patch of sky looking at loads of stars for a really long period of time to see some of them. It's hard. This is hard
It's really
stuff.
hard, yeah.
Yeah. We've only been doing that for what, since the late 1990s, is that right? Or is it the 1990s?
Yeah.
This is new stuff. I think we probably have time for maybe one more question if there is one. Otherwise we're done. Everyone's keen to get
We've
outside.
got one question.
One more question here.
Yeah, everyone wants to go and look up.
Exactly. Stop talking, I want to go
it's too
outside.
bright.
There's a question for Emily, really. With all the current focus, resource, effort going towards getting someone back on the moon, do you feel how will that help our wider understanding of the wider universe?
Are you in favour of putting people on the moon?
Well, my flippant answer is, of course, because I want to stick a telescope up there. Yes, absolutely. I think space exploration and astronomy do have a bit of a hand-in-hand relationship. The technologies that we developed for the James Webb Space Telescope ultimately came from some of the Apollo program technologies that were developed. So this idea that putting people on the moon is kind of a little bit just self-vanity, I think underplays a little bit the science that we do really want to do. There are really good cultural reasons why we want to go back to the moon, maybe set up a moon base, be part of our local system.
It's sort of what we do, isn't it?
It is, yeah. I mean, that's part of our human nature. We want to explore, to expand, to do something, even if it's hard, right, to misquote. But there's real science to do as well. I mean, the moon is this fossil of the early solar system, for example. It's dead. Nothing's happened to it. There's been no volcanoes. There's been no floods. There's been no dinosaurs pooing on everything. It's preserved.
That's Emily's knowledge of biology summed up in a sentence right there. But that'll do. It's
like I
close
said,
enough.
I've got a 4-year-old, so this is kind of where my brain sits at the moment. But so it preserves a really early part of our solar system that tells us something about how our solar system formed, how our planet Earth formed, that our Earth can no longer tell us because it's changed and grown and evolved. So even for that one reason, which is one among many, I think there's really a lot of really wonderful stuff to be done on the moon. And please let me put a telescope up there because that would be really cool.
There's something about human nature that says all of that's true, and can we just go and stand on it? Could we just go and stand on it? And I think that's a good thing. Listen, that brings us to the end of our allotted hour. So thank you once again so much for coming out on a Tuesday night here in York. It's been a pleasure talking to you. I hope to see some of you again on Sunday night, one last plug, 7:30 at the Ron Cook Hub. Otherwise, we might catch you at syzygy.fm for future and past podcasts. You can find all of our past episodes there. Thank you so much, York. It's been a really great night. Enjoy the rest of the festival.